Thank you, Mike. Is that too loud? I many times have to do this by raw voice, so I'm glad I don't have to shout today. You guys are a different audience than Altai region of Siberia, because I've been there. At this time of the year in the Altai, it's about 55 degrees below zero, and the wind is blowing, and you ought to see the Russian when he comes into the door. He walks like a big bear, and that's a lot what they say they are. Thank you for having me come over to this side of the mountain. I am normally this time of the year, I'm either in Europe or I'm someplace else talking about what is happening. Would you back up to the first slide?
Yep.
It is more than just strip till, and today I'm not going to talk about the mechanics of it. Dave Zimmer is going to speak a little bit about that, and I know that Troy Seaworth and other guys are going to talk about it. I want to visit with you about some of the issues about soil quality. Soil quality, please don't get the picture that it's only about what we do on doing biology. There's also some things that are really happening physically underneath the soils. I know that as I was involved with my master's program, I was in soil physics. And soil physics to a lot of people is horribly scary. But the physical characteristics that happen under the ground, that guys like Dave Deerstein and I that have looked at soils all these years, really start to change when you are affecting what we do, not only biologically, but what we do physically. Okay, so it is more about strip till, please. A long time ago in a galaxy far away, there was an elderly gentleman in 1965 that started our company that I worked for, Orthman Manufacturing, out of Lexington, Nebraska. And yes, I commute 300 miles from my house to the front door of our plant. And he hatched this idea about strip tillers. That is a 1984 picture of what strip till looked like in the Platte River Valley of Nebraska. As you can see, he was using a front-mounted 3-point system on an old Johnny Deere tractor, and behind it he was planting right into what he was doing, and that was hatched the idea. That same year, in Michigan, strip tillage got started, also with Ray, I'm trying to remember Ray's last name, I had it just a second ago. Ray Rossi, thank you. I still have ears to pick up those terms. Thank you. Next slide. So all throughout what was happening in the 80s and into the 90s, a good friend of mine, Lynn Fleming, got involved with developing a tool because of those things that you can see in the dark black were happening on the western plains of Nebraska, northern plains of Kansas, eastern plains of Colorado. High input costs were coming involved. Fertilizer was jumping and skyrocketed. Seed was starting to cost more money. As you know now, you start buying triple or quad stack corns and they're costing you $350 a bag. You can almost start thinking that every seed is going to cost you some value of money. Diesel prices were going up. The commodity prices were in the tank. We were seeing the $1.90 corn. Water limitations were coming involved, and then what happened in the late 90s in southwestern Nebraska, they went into a severe drought for 3 years. And then we felt it in eastern Colorado, and we felt it all over the world. The whole thing about soil stabilization, which I worked for SCS and then became NRCS, issues of erosion problems were just intense, where we were seeing sometimes 70 ton to the acre erosion events that were happening. And then more and more corn, GMO corn, which we were having BT involved, residues hung around for years and years and years. Next slide. The Orthman One Tripper, which is the tool that we sell and find that it's probably the one that works a lot in all kinds of environments. You can find it in Ukraine, you can find it in South Africa, you can't find it in South America, but you can find it in a lot of different environments, but we are all over the world. Next slide. I want to talk about 3 different stools underneath you as you sit down on that tractor seat, so to speak, those legs. Ideal seedbed preparation, quick, precision nutrient placement, and optimal root zone conditioning. Next slide. It's a whole thing about how we get a seed started, correct? We put that seed in the ground, whether or not we can get the germination to take off. We want that to happen with the moisture that's there, not having to pour a whole lot of them on it. When you talk about in Michigan, for instance, if they pump water in Michigan, they're putting on 42-degree water. If we pump water out of the Ogallala, we're pumping on 48-degree water. If we pump water that comes from the surface irrigation, maybe it might be warmer, especially in the summertime, versus we cool down that seed bed, we cool down the soil environment, we start slowing down growth below the soil surface. And I could go into it for a couple hours about root growth, and we are going to talk about root growth today. We don't have a seed bed that's warm, and it takes a certain soil temperature to get a seed to germinate, and then also to have both what we call vertical root development and lateral root development. You pour on 48-degree water, what happens to lateral root development? Almost comes to a halt. Vertical root development still might be there, but we know that it would be really changing. Next slide. So we got to have a quick start. We want to have what we call picket fence crop development. So it's for every seed that you drop, if you're dropping 32,000 seeds per acre, you want to have a seed about every 5 1/4 inches in a 30-inch row system. Next slide. This slide tells stories, and it has been all over the world. It happens to be from Colorado. The day before this slide was taken, it had rained 1 inch 10. The day of the slide, which is the day that was just the following day, it rained 70 hundredths in 30 minutes. This is 10 minutes after the rain is over. Strip till on the left, on the right is conventional tillage. The water was just pouring out into that field, and it took a while for that water to get in. But you can see that it was already soaking in. We've affected the water infiltration rates using strip tillage upwards of 9 times. We know that on this soil profile that it's supposed to have by NRCS irrigation manual standards of 3/4 inch per hour. That soil is absorbing water at 4.9 inches per hour because we're affecting porosity. And we'll go in and see the values of that. Next slide. It's an all thing about what we heard this morning from Troy and Eric, holding on to soil profile moisture. And we want to have that because if you start seeing if we are in the southern high plains of Texas, water's costing upwards of $75 an inch to apply, you start to think that every inch that we hold in that soil profile is very important. So that residue blanket that's over the top of that makes a whole lot of difference. Here a few days ago on the Front Range on into the plains of Nebraska and Kansas, we had some horrible winds. You get a wind run that lasts for 12 hours, running 35 miles an hour over it, it will pull water from 36 inches up to the soil surface. That residue stops a lot of that. You still get some, but it's pretty important to hold it. Next slide. So we see that this is a systematic approach. It's a whole thing looking farther beyond what you are doing when you're in the tractor seat. How many of you in this room, you don't have to raise your hands, believe that farming is in the tractor seat? A lot of you probably do, but that's where, when you get to talking with a lot of people over in Europe, they say, well, you do your best farming in the tractor seat, and I need to be there often. That is a misnomer anymore. It's more about what you're doing when you're thinking and getting things accomplished. So we know that with a systematic approach, we're being able to gain moisture, hold on to it longer. We've got reduced number of trips, which Eric showed. We're reducing pumping costs. We're helping keep salts from evaporating from the soil surface or soil coming up to the soil surface. We're helping roots follow a warmer and deeper profile to go down. And that is all about what happens. It's all about roots. You're growing something up above the ground, but where's all the water and the nutrients absorbed into this plant? 98-point-some-odd% of nutrients and water come through the roots. Next slide. So let's talk a little bit about the second leg of this milk stool that we sit upon when we're in that tractor seat. As you look at that tractor that's pulling that strip till tool, there is approximately on that tractor with everything that's in it, with the farmer, the GPS, $395,000 worth of goodies there. And then he's also got the fertility. Next slide. So we want to make the machine that we have function. with dry fertilizer, liquid fertilizers, ammonia, combinations of 1, 2, or 3. And it's all about how we get that soil prepared and put it in the ground with individual depth control from row 1 to row 12 if you've got a 12-row machine, and making sure that we've got all that spaghetti doing something that's doing something properly for the uptake of crop nutrients. Next slide. As you can see here, and I'm going to use this little red dot, it's not a bug running around, but we can apply, if we're strip tilling 10 inches deep, I think the battery's maybe going to go on this little guy, from there down to the bottom of the shank, we can apply fertilizer in a couple different spots. So we can apply fertilizer somewhere down here, and then somewhere in between or up closer to the soil surface. But there's a selection of reasons why we do it at 5 and 10 inches, and I'm going to go into that in just a minute. As you can see, that we have a nice opened up soil profile now. We haven't shattered it. We don't have huge voids. We don't want any of that because we want that plant root to start and stay in a consistent bed. Next slide. So as a diagram here is to give you an idea where we can place nutrients on number 1 and number 2. And it's very interesting. A lot of the people are now finding that we can also put liquid manure in. And we have a lot of growers in Germany and in England and in France and in the Netherlands that are putting down large sums of liquid manure with our system. They're usually pulling a drag hose with a big tank that's stationary, that they're holding upwards of 15,000 gallons of product, and they can use a drag hose for 500 feet and make this work very, very slick. Next slide. This is what I want to be able to tell you the reasons why crop physiology goes into this, and I've done a lot of study of it, but it's the issue of you're looking at a 40-day-old plant after germination, and we want to place fertility in 2 different locations because of what happens with the growth of that plant. And that red triangle that you see up above is when the plant was at about 15 to 20 days old. That's the size of the triangle that grows in this. This comes from several doctorate theses from Iowa State. And this pretty much goes with what the architecture of the corn plant looks like at that particular stage. So we look at that triangle, which is about 6 inches vertical by 13 inches on the bottom side of the triangle. The second triangle is the next 30 days of growth, and you can see that it's getting started, and it's about an 8-inch triangle from the tip of the top of the green to the parallel bottom, and then it's 18 inches across the bottom of that triangle. So architecturally, that root system looks like what your sons or daughter at about 3 years old that can take a crayon and make a Christmas tree, okay? So here's the top of the tree on top of the lower part of the tree. The center of that first triangle is about 3 inches to 4. The center of the second triangle is at about 9. At the stage of this growth of this plant, we know that it is setting some genetic switches to say, okay, I'm going to do this with the crop, and we're looking at a corn crop, and I'm going to do how many leaves, how tall it's going to be, all kinds of things happen. But we would place nutrients for the first set up at 4 inches to get that stage going, and then at this second stage, which is at 45 days after emergence. How many of you know a little bit about crop physiology on a corn plant? What happens at 45 days after emergence in a corn crop? It's about 18 to 22 inches tall. What happens physiologically? Anybody? Oh, we grow a lot of corn in Colorado. It sets the number of kernels around the cob. And it always sets in 2s. It's a diploid plant, so it sets in 10, 12, 14, 16, 18, 20, or 22. You feeding that correctly, and that switch is turned on, and says, okay, I'm going to have this number of rows be created, where hopefully we want to make those 2s multiply. So for every 2 rows that you have on that plant, and if you think that it takes to increase 1 bushel of yield on an 18-row cob, how many kernels extra do you have to have in a 32,000 plant population? 3 extra kernels. Now let's create 2 more rows. And the kernel of the cob is 40 kernels in length. we are jumping yield. Magnificent. It's all about where we put the nutrition. Next slide. So we want to place it so we know what's happening at the vegetative stage, and then we know that what I have in this dark, or this pale green area, is those are extra nutrients that hopefully were left over, and what happened with root exudates and all that kind of thing. So that pre-tassel stage, between 70 and 75 days, we know that that's where the ear stretch has been determined. And then the last stage, the more dramatic one, is very important, is the kernel set and fill and get ready to harvest. So we place nutrients maybe with a starter, and then one that is at 4 inches, and then one that is at 9 inches. These disseminate and spread through that part of the profile. We are constantly having the roots in a zone where they're being fed properly. And that's pretty important. Next slide. Now, the whole thing about guidance, I want to quickly go into this. As you can see, this is one of our tools that we put on planters. This is implement guidance for a planter. We put these big 30-inch blades in the ground, and they can help control where that thing is so that you're always plus or minus 1 inch if you're using RTK. So the first year that we did this study from Yuma, Colorado at the Irrigation Research Foundation farm, we looked at irrigated yields. And so if you're at sub-inch accuracy, where you're saying we're placing the seed 1 inch plus or minus from where we placed the nutrients, and you can see what the yield was. When we were 4 inches off that center, come on a little light, we were about 6 bushel down, and then 8 inches off in that first year, we were 10 bushels down. Then in year 2 and year 3, 5 other universities across the United States of America decided that we were going to do the same thing, similar study, and we looked at yields. We didn't talk to one another, but we were doing this study with cooperation with Trimble and John Deere, and we found that when you are 8 inches off, you're 30 bushels down the same year in year 3, and then in year 5. Year number 4, July 23rd came along, we had a hailstorm, 50-mile-an-hour winds, and it cut down the corn down to 3 inches in size. So we had no data whatsoever. But you can see, when you get past 4 inches away from your fertility, this plant is dropping yield tremendously. Next slide. Last part of this leg of the stool is optimal root zone conditioning. Next slide. It's the whole thing about whether or not our roots are really going to grow, and we take care of the compaction issues if you have some, eliminating subsoil voids, creating the beneficial pores, and I'm going to talk about that. Next slide. This is a picture from the National Soils Dynamic Lab at Auburn University. As you can see, compaction in the middle of that at about 12 inches. It's incredible. These are in megapascals compared to what Eric showed you in kilopascals. It's just moving the decimal point a couple spots. But you can see that water won't even go through that. Speaking of it, is really, really dense. If you think about it in pounds per square inch, if you're at 8 megapascals, you're looking at about 1,000 pounds per square inch that root is trying to force itself through. A corn root can force upwards of 400 psi when it's fully turgid. A sunflower plant can force at 1,100 psi. So they have a certain amount of strength issue. But you've got a soil here that's probably looking at something that's incredibly stronger. It's really going to struggle. Next slide. Then along come the researchers, and they started looking at how, if we use a tool to be able to condition that soil, 10 days after they strip tilled, and they used R1 tripper. I'm only showing you those, but they did it with comparison of 3 other tools. Well, we're not going to talk about those. You can see the cone index volume after 10 days. We had dropped it from 9 all the way down to about 1 megapascal. 110 days later, on the far right, you can see that the profile is still showing you evidence that we have improved the soil to the point that we're starting to see some reinsertion of compaction due to cultivation and some other things that are coming along. So it does have long-lasting effect from what we were seeing. The other models that they looked at 110 days afterwards, these red zones had squeezed shut. So it depends upon your shank and your tillage tool that you're getting accomplished. So I want to show you that strip till can have longevity. What happened out of this, that this was in peanuts, and they grew 250 pounds more of peanuts because they could harvest them, and also the peanuts could get deeper in the soil profile. Next slide. This is from the Irrigation Research Foundation farm. You can see here's where the tire track is. And this is in a more moist condition, but to give you an idea that when you get at 2.8 in a very moist soil, which is at field capacity, that is pretty dense. But here's where the strip till ran, and we're looking at it 100 days after the strip till ran. Across the bottom is the dimension of the size of that trench that we had dug, and then looked at soil tension every 2 inches using a penetrometer. Next slide. If I've done anything about what I've done over the last 34 years of looking at soils for the purpose of what's going on with growth of roots, we've looked at what happens with soil temperature and how the root profile warms up. This is conventional tillage, and by that I'm talking about 2 diskings, 1 chiseling, and a field finisher, and then you plant. This is strip till and then plant. As you can see, this is at about June 10th. The temperature is warmed up to 75 degrees Fahrenheit up there close to the soil surface, but this 55 degrees line, which is right here, this isotherm, is really important for cone development. Look at that, where that's how deep that is with this reverse bell. Compared to the conventional tillage, they all kind of get squished up here, right here at 8 inches at where the till zone is. But it's not as deep. That will show up here in a few slides. Next slide. So we want to use less invasive tillage. When we do till, we're only tilling every 30 inches, and it has that bell shape. Would you go back one? The tillage shape in the profile with the strip till tool that we use, called the Orthman 1 tripper, has this kind of shape. Some others will look a little bit different now. Go ahead. Whether we're strip till or direct seeding, we're observing a more ideal soil to root environment throughout the season. Next slide. Now, we're going to get into data. As you can see, this is that long-term study that I started way back in 2000 when I still worked for Uncle Sam. And you can see in the surface 4 inches, we looked at the organic matter that was going on in strip till versus a conventional tillage. And all of this is that kind of comparison. In 1999, 2000, when we soil sampled, our soil organic matter for the first 4 inches was 1.52. Look how it increased all the way to year 2008. This was a continuous corn study under pure irrigation, no grazing. Then down in central Nebraska, where the Orthman Research Farm is, we started at 2.25 and moved up to 2.6. It's a little bit slower in that kind of environment because of the clay. In a fine sandy loam, it seems to accumulate a little bit faster, but you can get an idea. Now go down to Central Texas. The reason I bring this data from Central Texas, we're looking at a burlesque, silty clay, 55% clay. This is called noontime soil. Anybody know what I mean by noontime soil? It's the best to till when you went to lunch. That's the best time to till it. Doesn't work any other time, but when you went to lunch, it does. The soil organic matter level was 1.3 and it changed to 1.49. When you can change a silty clay to 1.49 in 4 years in a cotton corn rotation, we've done something. And when you're changing organic matter from 1.5 to 2.2 or 2.2 to 2.6, those percentages, or those multiples, it's almost like a way you measure an earthquake. That's a lot of residue. As we heard this morning a little bit about, for every percent of organic matter, you're getting tons of residue, or tons of carbon in the soil profile. But I wanted to give you an idea that this is the kind of stuff that we can make a difference in your soil profile without adding cover crops into it. And when you're in the central part of Texas, this is hot and dry country where the soils are constantly very warm. It's hard to, in a rotation like that of cotton and corn, to keep residue in and on the soil surface. Next slide. One of the things that I like to look at, soil pores. Get a hand lens and look at your skin and look at those soil pores. So the pores that soil scientists look at a lot are 3 different sizes that we can visualize and find. less than 1 millimeter, 1 to 2 millimeter in size, and 2 to 5. The 2 to 5 are the large ones. Usually a vertical type boring earthworm will grow in that kind of a pore size. This is at 27 different sites on our farm, looking at no-till versus strip-till, which we do quite a bit of comparisons. And this is after a 4-year no-till strip-till study. And we looked at between 2 and 6 inches depth, a 4-inch block, which we call 1 decimeter. We looked at the size and then counted all of those pores. Drives you nuts, don't it, Dave? Deerstein's over there smiling like a Cheshire cat. But under no-till and strip-till, we're getting a lot of the very fine pores, which is consistent. But look at the number of this in this column, 1 to 2. That particular soil pore releases water more readily to the soil, to the root, than any other pore. When they get really big like this, they're a big droplet, and gravity pulls the water and moves it on down through the soil profile. Maybe the root can't get access to it quick. But in this size, because of cohesion and adhesion of water in that soil pore, releases the water to the root system. And what we find with a lot of no-till systems, especially if they are large farmers and they're still driving their grain cart all over the place and their sprayers and it's crisscrossing all over, compaction starts to ensue. These pores break down in the no-till system, but we can keep them maintained in the strip-till system because we help integrate lesser compaction issues and we start seeing the bulk density improve. This happens to be, we're showing a fellow from Venezuela, what's going on when we look at soil pores. Next slide. I want to look at that, some data a little bit differently. If we looked at, these are all pore sizes. The blue is the finest, which you can see up here in the upper right-hand corner. The medium-sized pores, that 1 to 2 millimeter, and then the large-sized pores. But if you look at the strip-till and the mean of all those pore holes that we looked at, we're looking at a lot of data here. We've probably got 29.7% more pores in the strip-till than in the no-till, and you can see 41% more, 40% here. I'm trying to show you that we're helping improve, especially these in the little red blocks. Next slide. So we look at it on the high side of the numbers. We did a range, and we'll find that you'll have anywhere from 100 pores and then up to maybe 400 pores. But this one was 375 total pores. Getting an idea that the strip-till, the no-till high numbers are better than the strip-till mean, so we are still doing a good job with this. And these pores make a whole lot of difference. Next slide. Some of the actual numbers that came from a study in 2003 to 2006 at the Irrigation Research Foundation farm in Yuma County, Colorado. You can see the range of numbers of the pores. We looked at 15 different decimeters in those plots. So the conventional tillage looks like this, and then the strip tillage is more. So we're affecting soil porosity. Next slide. The whole issue of bulk density, weight per gram, per cubic centimeter, gives you an idea of density per soil, so it's telling you whether there's pores in there or we're compacting it. At the Irrigation Research Farm in an Ascalon sandy clay loam, which has about 23% clay, we started at 1.43 in the long-term strip till, and we changed it, went to 1.4. That is a dramatic improvement over those 6 years. Go over the conventional tillage, you can see it stayed very static in the row and in the furrow. So we were taking bulk densities from both sites. These are bulk densities at 7 inches depth, approximately the plow pan depth. Furrow here changed, dropped 1/10. That is immense. From here, stayed very stable. Okay, next slide. Let's go to Texas. Corn on corn, high clay soil, 55% clay, something that you guys see over here in the Gunnison and the Pagre area. In the hard row, that means that's the row where the traffic went. There it is, 1.7, thereabouts. And in the soft row, 1.45. As you can see, the changes from conventional to strip till to no-till. And then in the cotton and corn, it varies quite a bit, going back and forth because of the rooting pattern and how tillage was being affected or not affected, whether or not they were putting on certain herbicides, and it also happened to be that what's going on the year before, whether it's dry or not. These are very hot soils. They're thermic soils. For those of you that know a little bit about that, what that means, they don't get any freeze and fall, nothing to break it up. If it does get compacted, it'll stay there for thousands of years. Next slide. Two years later, come back and we did the same study in the area. We had located these by GPS, so we could come back and do bulk densities. There is a change. The strip till was improving, but very slightly. The no-till was improving, but very slightly. Corn on cotton, we had a little bit of improvement, but not very much. But you can see that the tillage effect is making a difference. These were getting worse in the conventional tillage. Next slide. Now, we all want to know what happens on the surface, because all of us come along and we kick the dirt. We'll call it dirt for the moment. And we can see whether it's wet or it's dry or it's real dusty. Do we get a crust? All of those kinds of things. Soil aggregate stability, which is a slate test that NRCS talks a lot about in their whole thing about soil quality. This is looking at that in a 53% clay, low soil organic matter. And you can see we did it in hard row versus soft row. We've sampled it in 08, 09, and 10. If it has a value of 5, it's very good aggregate stability. If it has a value of 1, it's kind of if it's a value of 0, it means it turns to mush in a very short period of time. And it's all measured, and we look at tens of samples when we do this. You can see some of the difference between the hard row and the soft row. When you have an average of 4.6, that means those aggregates are very stable. In the year 2009, they dropped a little bit because of the crop rotation and also the way the year had been. And then in 2010, it came back up. So this changes year to year. And I think that we need to evaluate that and keep that in mind. In the hard row, in the conventional tillage, look at the deterioration from 08 to 09 to 10. Aggregate stability was falling apart. Same thing in the soft row, 3 to 1 to 0.9. It was just turning mush. In fact, we would drop that clod in the soil, and within 30 seconds, it was mush. It totally fell apart because you watch it for a certain number of minutes of time to make that happen. But to give you an idea that in the strip till and the hard row, no-till, these are very, very comparable. They stay pretty stable. They're starting to improve. So it doesn't happen overnight, but to give you an idea that as we do conservation tillage, going towards a direct seeding method, we are improving the soil profile. And we're helping in a very heavy textured soil. Next slide. Soil porosity down there at the Stiles Farm, where we're doing this research. This is looking at, again, those number of pores that on a square decimeter. You can see in 2007 to 2010 in the strip till, how our rotation changed some. You can see that we were having pores in the hard row decrease. Pretty much the same thing across the no-till, and then in the in conventional tillage, it stayed very stable. But let's watch what happens in the 1 to 2 millimeter. They're going up, and they're staying stable or falling off. In the soft row, here's where strip till starts to show it's staying pretty stable with over those 4 years. No-till staying pretty stable. Conventional tillage, it's all over the board, but we're getting the pore sizes improving in the 1 to 2 millimeter size. It's very important on how water will infiltrate and go into the depth of the soil. Next slide. So we acknowledge that what we're doing with strip tillage in no-till and conventional tillage has to be a systematic approach. And we think about this worldwide, you know, it has a whole lot of a soil appearance to it, but what's going on when you start thinking about what Eric and Troy are doing at Colorado State University, they're trying to put it together, and how does it work for the grower, economic-wise, soils-wise, water quality-wise, whether or not we're doing good for the protection of the soil by erosion, all of those things. But there's other things that we have to look at, and those facets, those are hybrid selections. I'm going to show you something here in just a minute about that. Knowing the rooting patterns, especially in corn. How many of you know that there are lots of different root architectures in a corn crop? Does corn always have one root pattern? This whole thing about improved fertilization, I talked about that early on. Putting the nutrients in the pathway of the root is incredibly important. We can decrease the quantity of product that we have to put on, especially when we use better quality of fertilizers. I might hurt somebody's feelings, but folks, 1034 isn't all what it's cracked up to be. There are better products out on the market than that, especially in a saline environment. Improved pest and nutrient issues. Irrigation water management is important to this tremendously, especially in irrigated agriculture, and residue management. Next slide. So growers want to know the ideal environment. What does it take to get it all the way up to maturity? Next slide. Here is a root system comparison with one particular root architecture of a corn plant. At 25 days between strip till and no-till, that's 25 days after it emerged. You can see the root system isn't a whole lot different, but there is some, for those of us that look at roots crazy-wise. Then at 55 days, the corn now is chest high. You can see that the root system is getting deeper with the strip till versus the no-till. Partly is because the soil is still a bit cool longer. But then when we get further on, at 105 days after emergence, the corn is it's fully tasseled, it's fully silked, the kernels are probably beyond milk stage going into dough. You can see how that root system is now extending below 48 inches if you have a very deep soil. But where's the major part of the root system in this corn plant? Under the strip till, it's down here at about 32 inches. Under the no-till, it's way up here at about 18. 18 to 32 is how many inches? It's 14 inches. In 14 inches of a clay loam soil profile, we have approximately another gallon to a gallon and a half of water available to that plant from where that root system can draw. That's a lot of potential bushel. Next slide. I told you about soil architecture, root architecture. Right now, all the roots that I've looked at, over 1,530 different profiles of root systems. These were the first 3 up until 2012. Another guy came into the picture. So we call this one the carrot, this one the umbrella with stringers. This is an umbrella because you have the shaft to be able to hold the umbrella. And there's the horseshoe. What happens? We apply nutrients right underneath the plant, about right there. The strategy of how that plant's going to feed itself and how it's going to water and everything else changes the ballgame. Dr. Martin Bone with the University of Illinois is a corn physiologist. He said this one is intriguing to him too. He's done a lot of root studies and looking at architecture, and he is taking pictures of it from 3 dimensions and doing fractal designs with root architectures. And when Martin and I start to talk about it, everybody else wants to get out of the room because it goes crazy. We get so excited about what's going on with this. But how many of you, if you think about it, let me give you a scenario. You've got a wet soil that stays wet until about July, and then we start putting irrigation water on it. What root system would you want to put into that particular environment? 1's on the left, 4's on the right. 1, 2, 3, or 4. I need a little volunteer here to say yes, no, number 1, number 2, number 3, number 4. Come on, there we go. Dave says number 1. He's probably right. It could be either this one or this one. It would work in that environment. let's say it stays wet all year long, you're in Ohio, 15 miles away from Lake Erie. You put on all kinds of manure. It rains cats and dogs and pitchforks and everything else. Which root system would probably work the best in that environment? Number 3. Very good. So what we have for root systems, tillage, fertilizer placement, starts to make a difference on how you can take this and understand a little bit better about when you go to your seed catalog and you talk to your Pioneer, your Syngenta, or your DeKalb person, to name the big 3, you can start saying, okay, guy, give me some information about how I can really grow a better crop. And do you know, Mr. Seed Salesman, do I have this, or this when I buy that seed? They will probably, they'll do some switching and scratching. They don't know. One company is starting to get involved with it. I won't mention that name, but they're really starting to find out because they know that this seed hybrid right here that you find came from Indonesia. It's a fairly recent one on the market. And that particular seed company has the majority of their seed that they sell from that particular rooting system. This works in irrigated agriculture with deep to very deep soils unless you've got a lot of salinity down somewhere in here that is accumulating. Next slide. So, trying to give you an idea as we wrap it up here to get ready for Dave to come up. We are putting strip till across the globe, and we're trying to help growers to know, as a company, working with different universities and research sites. In fact, we're working right now, Orthman manufacturing with 18 different research facilities across the nation and 3 overseas to study strip till. How does it affect the grower? What is it doing? What's going on in the soils? All those kinds of things. Next slide. I say that it's a tough act to follow. That's partly because we have a particular market guide that says that. But we want to really see that smart conservation tillage methods are working. They work over here on this side of the mountain versus over on the other side of the mountain. There isn't very much strip tillage going on in between. That's for darn sure. But when you ride on a tractor with a grower from Ukraine and ride on a tractor from a grower from Johannesburg, South Africa, and they're farming with strip tillage, we're farming with the same kinds of mentality, but we're still not farming the same kinds of mentality. Folks in this room, when they come over here to the United States and they see what we're doing on the west slopes of Colorado, they believe that they've just gone home. They see this environment work the same way it does over there for them. South Africa has, most of it is quite arid. They grow corn at 5,000 feet elevation. Now it's 23 degrees south compared to where you're at here at about 39 degrees north. We're getting an idea that they can make things happen there as we do here in the United States. So I'll open it up, Mike, to questions.
Any questions for Mike?
I could run on for another 3 hours if you like, because I've got about 7 other presentations that would blow your mind.
Hey Mike, this isn't a question necessarily as a comment, but both Eric and you used some soil clothing penetrometer data to illustrate compaction, which is a pretty useful, easy tool.
Yes.
To identify compaction. So I went out to the truck and robbed them. If you want to maybe demonstrate to people how they use. That one's more complicated because it has a logger, but you can get a real simple one with a dial on it.
Yeah, you can get one from Dickie John.
For what?
It's $120 retail. When you're using one of these machines, you do not want to go out there with the eagerness to say, I want to shove this thing like I want to do it to the President of the United States or something like that. Good, I mean, I understand there's a few guys in here that have got a sense of humor this morning. Okay, when you're moving this, you want to check the soil moisture before you do it, and in the zone where you're going to look and go to what particular depth. That soil moisture should be no less than 25% depleted of its field capacity. If you get more than that, What you're actually finding is probably just dry zones. So the next thing is you get onto it, I'm not going to push it, but put it into the soil and push it at approximately 1 inch per second. Now, what they have at National Soils Dynamic Lab, they're using a hydraulic probe that is pushing at that particular rate, and they can keep the pressure up. So you get to compaction, and those of you that eat more than I do and don't ride a bicycle as much as I do, you have some weight to be able to push. I have to get on it and almost have to stand on it. What happens with that mechanical dial that this one has got a digital dial? You'll watch it just go whoosh, and go clear over there to 300 psi. And it'll just show you, wow, I got some huge compactions in there. Well, that's because you had a little bit of heft to be able to push it to the ground. Push it at 1 inch per second at a very steady rate, and you'll get an idea. It takes effort to get it in the ground. But that'll tell you what it is when you're using this. Does that help, Troy? Eric?
A lot of have some perspective where the numbers came from.
Right. But this tool is using it's approximately, it used to be, 1/2 of an inch in diameter. And it's been used frequently. You can also get a finer tip. But these are all got a lot of background in their testing and what they use. But that's how we use the soil penetrometer. There's also, Dear Stein, do you have one of the little pocket penetrometers that you use? He shakes his head, yes. It's a little 1/4 inch shaft. It's done with springs. You can get the springs to a certain tension, and you can poke them into the soil profile. They move in approximately 1/4 inch, and you make the measurement. With this, you want to do it very steady, and you can get a chance to